In this video we're going to start CC11, which is a paper one only topic, and it is on obtaining metals and using metals. This first video is all going to be about the reactivity of metals, the different reactions that metals undergo. And if we're going to be talking about the reactivity of metals, there's one thing that we need to be super clear on, and that is metals always lose electrons when they react. So anytime an element is involved in a chemical reaction, you are talking about electrons, whether they're losing or gaining or sharing electrons. In the case of metals, they are always going to lose electrons when they react. And if we look at a typical group 1 metal, sodium, we can see why they do this. So sodium is in group 1, it's got a mass number of 23 and an atomic number of 11. If I want to know how many electrons sodium has, I look at the atomic number, and I've drawn an electron shell diagram for sodium. I've put 2 electrons in the first shell, 8 electrons in the second shell, and then 1 electron in the third shell. That fits what I would expect. It's a group 1 metal. It should have 1 electron in its outer shell. Now for sodium, the outer shell, which is the shell furthest from the nucleus, is the third shell. The third shell can hold 8 electrons. Sodium has only got 1, so it does not have a full outer shell. It's got 2 options to get a full outer shell. It could either gain another 7 electrons so that the third shell has 8 in total, or it could lose 1 electron, in which case the second shell will become the outer shell. Metals always lose electrons, and the reason is it's not stable for sodium to gain 7 electrons. That would give it a charge of -7, and that's incredibly unstable. So it's not going to gain 7 electrons, it's just going to lose 1. It's far easier for sodium to lose 1 electron than to gain 7. And as I said, when it loses 1 electron, instead of having 11 electrons, it's only going to have 10. So when I redraw sodium, I only have 10 electrons to draw this time. I put 2 electrons in the first shell, I put 8 electrons in the second shell, and that's my 10 electrons drawn. I don't need a third shell. The second shell becomes the outer shell. The second shell is full, so sodium has lost 1 electron and ends up with a full outer shell. Because it's losing an electron, it is going to end up with a charge. When they lose electrons, they always end up with a positive charge. You're losing a negative electron, you end up with a positive charge overall. All group 1 metals will do the same. They all have 1 electron in their outer shell. They all lose that electron to have a full outer shell. If I look at a group 2 metal, we're going to see something similar. So I've drawn magnesium. Mass number of 24, atomic number of 12. It's the atomic number I look at for the number of electrons. So I've got 12 to draw, 2 in the first shell, 8 in the second shell, 2 in the third shell. Again, this fits what I would expect to see. It's a group 2 element. It should have 2 electrons in its outer shell. Again, its outer shell is the third shell. The third shell can hold 8 electrons. Magnesium has currently got 2. It does not have a full outer shell. It could gain 6, or it could lose 2. Again, gaining 6 would give it a charge of -6. That's very, very unstable. So it's not going to gain 6. It's far easier to lose 2 electrons, because when it loses 2 electrons, instead of having 12, it's only going to have 10. And when I draw magnesium with 10 electrons, I can put 2 in the first shell, I can put 8 in the second shell, and that is the 10 electrons drawn. Again, the outer shell is now the second shell. The second shell has 8 electrons, so the second shell is full. So by losing the 2 electrons in the third shell, the second shell becomes the outer shell. The second shell is full. Because it's losing 2 electrons, it's going to have a charge of +2. All group 2 metals will react in the same way. They all have 2 electrons in their outer shell. They will all lose 2 when they react. If you had a group 3 metal, it would have 3 electrons in its outer shell. It will lose 3 electrons when it reacts. So in this topic, we're going to look at the reactivity of metals, so which metals are the most reactive. And in general, the easier it is for metals to lose electrons, the more reactive the metal will be. So when we're comparing sodium and magnesium, we see sodium loses 1 electron when it reacts, but magnesium loses 2. So you need to ask yourself, which is going to be easier? Is it easier to lose 1 electron, or is it easier to lose 2? And the answer is it's going to be easier to lose 1 electron. Okay, because it's easier to lose 1 electron, that means sodium is going to be more reactive than magnesium. If you had a group 3 element, it would have 3 electrons to lose. So losing 3 electrons is harder than losing just 1. Therefore, your group 3 metals are not going to be quite as reactive. And we have what we call a reactivity series, which you do need to learn. And this is the common metals that we study at GCSE are put in order, with the most reactive at the top and then the least reactive at the bottom. So it can be intimidating, this long list of metals to try and learn off by heart. But if we take a closer look at the list, you'll see the top 3 metals, potassium, sodium, lithium, they are all in group 1. After group 1 metals, I've got calcium and magnesium, which are in group 2. And then I've got aluminium, which is in group 3. So it's what we talked about before. Group 1 metals are more reactive than group 2, and group 2 is more reactive than group 3, because group 1 metals only need to lose 1 electron, whereas group 2 need to lose 2 electrons, and group 3 need to lose 3 electrons. It's easier to lose 1, therefore the group 1 metals are the most reactive. However, you can see that I've got 3 group 1 metals, potassium, sodium, and lithium. How do I know that potassium is the most reactive and lithium is the least reactive out of those group 1 metals? Well, again, it does come back to the statement I've written before. The easier it is for metals to lose electrons, the more reactive they will be. So if I compare 2 group 1 metals, I've got sodium and I've got lithium. Again, they're both group 1 metals, so they both got 1 electron in their outer shell. They are both trying to lose 1 electron when they react. But I have to ask myself, which is going to find it easier to lose the electron, lithium or sodium? So if you look at the 2 metals, the kind of most obvious difference between them is their size. Sodium has got 3 electron shells, lithium has only got 2. So sodium has got more electron shells. And that means that the electron that sodium is trying to lose, which is this outer shell electron here, the outer shell electron is then further from the positive nucleus. Because the nucleus is positive and electrons are negative, there's an attraction between the electrons and the positive nucleus. Because there's more electron shells in sodium, that outer electron is further from the positive nucleus. There's less of an attraction, and therefore it's easier for sodium to lose an electron. So I would say there's more electron shells, so there's less attraction between the outer electron, which is the one you're trying to lose, and the positive nucleus. Because there's less attraction, it is easier to lose an electron. So sodium is going to find it easier to lose an electron than lithium. If I drew potassium for you, potassium, I'm not going to draw the whole thing out, but it has got 4 electron shells. It's even bigger than sodium, which means its outer electron is even further from the positive nucleus, making it even easier to lose. So if I go back and look at my reactivity series, we've got the group 1 metals at the top, then group 2, then group 3. But if we look at the group 1, I've got potassium as the most reactive. Potassium has got 4 electron shells. Then I've got sodium with 3 electron shells. Then I've got lithium with only 2 electron shells. So the bigger the metal, the more reactive it's going to be, because it's easier to lose that outer shell electron. If I look at my group 2, calcium also has got 4 electron shells. Magnesium has only got 3 electron shells. So again, I'm taking the bigger group 2 element and putting it in front of the slightly smaller group 2 element. And then I've got aluminium, the only metal from group 3. So you may ask, how did I know straight off how many electron shells they had? That information can be got from my periodic table, okay? Periods are these rows that go across. The period number tells you how many electron shells. This is period 1 with hydrogen and helium. Period 2 contains lithium. Period 3, sodium. Period 4, potassium. Because potassium's in period 4, it's got 4 electron shells. Magnesium's in period 3. Remember, it's not 1, 2, it's 1, 2, 3. Therefore, it's got 3 electron shells. So that's how I know straight off how big they are, how many electron shells they are, without even drawing them. So you've got group 1 at the top, then group 2, then group 3. After that, the reactivity series, You're just going to have to learn it, okay? There are two non-metals in the reactivity series. You've got carbon and you've got hydrogen. So if I look at my periodic table, hydrogen, yes, it's floating around in the middle, but it is a non-metal. And I've got carbon over here. So I've got two non-metals in my reactivity series. And it's very important that you know exactly where they go. We're going to come back to why they're included in the reactivity series in a later video. Other than my non-metals, you then got zinc, iron, copper, silver, and gold. These elements are all found in the transition metals. So I've got iron in here, I've got copper here, zinc here, I've got silver, and I've got gold. So they're not in the main groups, so we can't use the same rules to explain why zinc is more reactive than copper. In this case, you're just going to have to learn it, okay? It goes zinc, iron, copper, silver, gold, and you need to know where carbon fits in and where hydrogen fits in. Beneath here, I've just got two worked examples, okay? Why are group 1 metals more reactive than group 2? Say what they need to do to react. Group 1, lose 1, group 2, lose 2. And then it's easier to lose 1 than to lose 2. Potassium, sodium are both in group 1. Why is potassium more reactive? More electron shells, outer electron is further, reduces the attraction, easier to lose. To be fair, that question typically comes up more from CC13, which is a paper 2 topics called groups. Now that we've looked at which metals are the most reactive, we need to look at the actual reactions that metals undergo. And you've got 3 that you need to look at. You need to look at how metals react with water, how metals react with acids, and displacement reactions. So I'll go through an example for each of the 3 reactions. So the first of the 3 reactions is the reactions of metals with water. Again, this is something you would have seen when you studied the alkaline metals as part of CC13. So I'm going to take the most reactive metal that we have in our series, potassium, react it with water, and the products formed are going to be potassium hydroxide and hydrogen gas. If I change that metal to sodium and have sodium plus water, I'm still going to form a hydroxide and hydrogen gas, but instead of forming potassium hydroxide, I am now going to form sodium hydroxide. If I change that metal to lithium and react lithium with water, again, I'm still going to form a hydroxide and hydrogen, but because lithium is my metal, I'm going to be forming lithium hydroxide. So if you react a metal with water, you get the metal hydroxide plus hydrogen gas. One more example, if I use calcium as my metal, I react it with water, I get calcium hydroxide and I get hydrogen gas. So these 3 reactions, potassium, sodium, and lithium, you study them as part of CC13. You need to be able to describe what you see during this reaction. Because you're making hydrogen gas, you are going to see fizzing or bubbles. You also see the metal floating or moving across the surface of the water. And in the case of potassium, you see a lilac flame. So these are reactions that you do need to know in detail from another topic, exactly what you would see. You'll notice I started with the most reactive metal there, potassium, then I did the other group 1 metals, and then I did the most reactive of my group 2 metals. So if I'm looking back at my reactivity series, I've shown the reaction of potassium, sodium, lithium, and calcium, the top 4. If I went further than that, I went down to magnesium, I'm not actually going to see anything with water. So as you move further down the reactivity series and the metals get less and less reactive, they don't react with water. Water is not reactive enough for them to properly react with. So it's only those top 4 metals in your reactivity series that you're going to see a reaction with water. And in every case, you get metal hydroxide and you get hydrogen gas. The second set of reactions is the reactions with acids. If you react a metal with an acid, you will get salt and you will get hydrogen gas. Now, it's not enough to just write salt. You need to be able to name the salt, and the name of the salt consists of 2 words. The first word is just the name of the metal. The second word will depend on the acid you use, and we learn about 3 acids at GCSE. If you use hydrochloric acid as your acid, then your salt will end in the word chloride. If you use sulfuric acid as your acid, your salt will end in sulfate. And if you use nitric acid as your acid, it will end in nitrate. So again, I'm just going to do a few examples. So I've got my metal, magnesium, and I'm reacting with hydrochloric acid. It is going to form a salt. I need to be able to name that salt. The first word of my salt is just the metal. In this case, magnesium is my metal, so magnesium is the first word in the salt. And the second word is going to come from my acid. If I've got hydrochloric acid, then the ending of the salt will be chloride. The salt I'm forming is magnesium chloride. And then my second product is hydrogen gas. So again, just like the reaction with water, I'm producing hydrogen gas. So I'm also going to see fizzing in these reactions. The next one, this time my metal is aluminium. So the first word in my salt is now going to be aluminium. And instead of using hydrochloric acid, I'm using sulfuric acid. So it's not going to end in chloride, it's going to end in sulfate. So I get aluminium sulfate as my salt. And again, I form hydrogen gas. The last one, I've got iron and nitric acid. So iron is my metal, so the first word in my salt will be iron. If I'm using nitric acid, my salt ends in nitrate. So it becomes iron nitrate is my salt plus hydrogen gas. And again, as you're producing hydrogen gas, you are going to see some fizzing. You might notice with these reactions that I started with magnesium. So I chose to use magnesium, and then I used aluminium, and then I used iron. I didn't use potassium or sodium. And the reason is acids are already reactive. And if you chuck in a really reactive metal into an acid, it can be explosive. So potassium, just reacting with water, already produces a purple flame. If you're going to throw potassium into an acid, the reaction will be very violent and it will be unsafe. So if I wanted to react my metals with acid, I wouldn't choose potassium. I would start with magnesium and then move my way down the reactivity series. Just a worked example here. Describe a safe test to show that potassium is more reactive than sodium. If I wanted to show that potassium is more reactive, I'm not going to throw potassium and sodium into an acid, okay? That would be very violent. So if I want to compare their reactivity, I'm going to put potassium and sodium into water, and then I will compare that reactivity that way. If you had two metals and you didn't know what metals they were, and you wanted to test the reactivity, again, you would never just add them both to an acid. That could be too dangerous. You would start by adding them to water. So our third type of reaction with metals are called displacement reactions, and that happens when you take a metal and you react it with a salt solution. And again, the easiest way to show these is just to give you an example. So here I've got my metal, sodium, and my salt solution is copper nitrate. So because it's a solution, this would be a salt dissolved in water. If I were to add a state symbol to copper nitrate, it would be AQ. It's a solution. So I take my metal, sodium, and I add it to copper nitrate. And the rule is that if the metal that's by itself, so in this case sodium is by itself, it's not bonded to anything else. If the metal by itself is more reactive than the metal in the salt, then they're going to switch places. So the metal by itself is sodium. The metal in the salt is copper. If sodium is more reactive than copper, they will switch places. And when you use your reactivity series, you will see that sodium is right up here at the top, whereas copper is down here at the bottom. So sodium is more reactive than copper. That means they're going to swap places. And when they do, the sodium is going to be bonded to the nitrate and the copper is going to be left by itself. So sodium is more reactive than copper, so sodium takes copper's place. If we look at another example, this time magnesium is the metal by itself, and I'm reacting magnesium with silver chloride. So silver is the metal, so I'm comparing magnesium to silver. Is magnesium more reactive than silver? The answer is yes. Because it's more reactive, they swap places. Magnesium pairs up with the chloride, and then I've got silver left by itself. One more example, this one got magnesium and calcium chloride. So magnesium, the metal by itself, calcium, the metal in the compound. And if we go back here, we'll see that calcium is here and magnesium is below it. So calcium is more reactive than magnesium. Because calcium is the more reactive metal, then these two cannot swap places and you get no reaction. So there's no reaction when they cannot swap places. So at this point, I want you to take a second to do some questions. I just want you to do those questions there, 17 down to 20. So press pause, have a go at the questions, and then press play when you are ready to see the answers. Okay, so going through the answers, the first reaction will take place. Calcium's more reactive than magnesium, so calcium and magnesium swap places. Zinc is more reactive than iron, so they swap places. Gold, the metal by itself, is not more reactive than copper, so you'll get no reaction there. Potassium is more reactive than zinc, so they'll swap places. Copper is not more reactive than iron, no reaction. Iron is not more reactive than lithium, so no reaction. And then the last one, magnesium, is more reactive than iron, so they will swap places. So again, to do these, you're going to have to look at your reactivity series. If the metal by itself is more reactive than the metal in the compound, and then they'll swap places. When copper is added to lithium chloride, no reaction takes place. Explain why this is the case. So copper is the metal by itself, lithium is the metal in the compound. All you would need to say is copper is less reactive than lithium. Or you could say lithium is more reactive than copper. That'll get you your first mark. To get your second mark, you will say copper cannot displace lithium. So displace is just the word we use for cannot take the place of. So copper cannot displace lithium because it's less reactive than lithium. There's no point using cold water if you want to compare the reactivity of copper and aluminium, because copper and aluminium, they won't react with cold water. Okay, sulfuric acid should not be used to compare the reactivity of sodium and potassium because the reaction would be too violent or too dangerous. Okay, these are two of your most reactive metals. You're not going to add them to an acid. So you could use the acid to compare copper and aluminium, and the water to compare sodium and potassium. In the next video, we're going to look at the displacement reactions in a little bit more detail, because we need to look at what's happening with the electrons during a displacement reaction. So we're going to look at how displacement reactions are examples of redox reactions.